This point, we've been doing projections, but what we've basically been doing is saying, hey, there is no initial velocity up or down. We've only been talking about things that have an initial velocity horizontally. So our drone drop that he got blown around in, there was only horizontal movement there. Or if something gets like pushed off of a cliff, the velocity that it's getting is just horizontal. They're not actually throwing it up or down off the cliff up until this point. So what we're gonna actually introduce now is projections at an angle. Most projections in life are going to be at an angle. We've given examples of ones that are not. But when you think of other examples like shooting something, shooting an arrow or hitting a baseball, those are definitely not just horizontal movements on those. And so now, up until this point, we have had an initial velocity vertically of 0, but it is no longer 0 when it is done at an angle. All right? So our initial velocity for y, which is why you'll see this little base component here, velocity of y initially, that's what all that means, is now no longer going to be 0. It's going to be based on the whatever is happening to the object. And so at this point, we have to calculate our velocity. All right, so we have to take two pieces that are affecting the movement of this. We have an initial horizontal velocity and an initial vertical velocity. You'll notice that horizontal velocity doesn't have that I, and that's because horizontal velocity is not going to change. We are still talking about things that do not have their own propulsion, okay? So if I was talking about a rocket that had its own propulsion system, then my horizontal velocity may in fact change over the course of it, right? But I'm not talking about that. I'm talking about something that has an initial velocity and then it's let go. So my horizontal is just, it is what it is. However, you'll notice your vertical does have an initial because on Earth, we always have a vertical acceleration going on called gravity. And so we are going to have to take that into account for our vertical, just like we did when we did the drops, right? We had to account for the gravity there. And so we're going to use the same concept that we used when we did vectors. You take that initial velocity that it gives you, you multiply it by the cosine of whatever angle it is being launched at, and that is going to be your horizontal velocity. For your initial vertical velocity, you're going to do the same thing, but you're going to use sine. Okay, so your horizontal is going to use your cosine, your vertical is going to use your sine, which is exactly what we did when we did vectors. The first thing we're going to do is we're actually going to graph this. So we have the projectile's vertical and horizontal position coordinates, and they are determined from the position forms of the equations of motion. So we're going to go back over the equations of motion. But then you can create ordered pairs based on what you're comparing. We're going to actually compare a couple things in our first example. If you include time in that, they're called ordered triples. So you can compare time to one thing and time to another. But if you're comparing time to two different movements, then you have three. You have time, you have your X movement, you have your Y movement. And so you can compare any multitude of things at one time. And we're going to do an example where we do two different graphs for the same thing. So here's the example. An archer shoots an arrow at an angle of 45 degrees above the horizontal with an initial speed of 41.6 meters per second. Plot the vertical velocity of the arrow versus time for every second. And then plot the height of the arrow versus the range every second for 6 seconds. All right. So we're looking at the first one, vertical velocity versus time every 6 seconds. So let's talk about what vertical velocity and horizontal velocity look like for this. So the first thing I would do is I would probably go ahead and figure out that horizontal velocity and figure out that initial vertical velocity. So we're going to do that using our formulas that we were just given. We're going to take our initial velocity that they gave us times the cosine of theta. So the initial velocity that they gave us is 41.6 meters per second. So I have 41.6 meters per second, and I'm going to take that and multiply by the cosine of the angle that they gave me. And the angle that they gave me was 45 degrees. 45 is a nice one because it has the same sine and cosine. So when I multiply that out, I'm going to get approximately 29.41 meters per second. You'll notice if you ever see the calculations, they'll often take it out multiple decimal places just so that they can keep it as close to as possible, but then they're underlining what would actually be your significant digit there. Just so as you track it, your brain always goes back to your final answer being significant digit. What we're actually looking at is how quickly is it being displaced horizontally, how quickly is it being displaced vertically, because it's leaving at an angle. And you don't just split it in two, as you can clearly see. You don't just split it in two. For my pre-cal folks, that's square root of 2 over 2 for sine and cosine. So it's actually a little bit bigger than 1/2. Square root of 2 is larger than 1, right? And so it's actually moving a little bit different than what you would think would split straight down the middle. Even though the angle splits it straight down the middle, the movement does not. So we do exactly the same thing for vertical. Now, don't get confused. They did use 45 degrees, which does have the same sine and cosine, but these will not always be the same. In fact, the only time they're the same is when it's a 45-degree angle. Any other time, they're going to be different. They just happen to be the same because of the angle that they have chosen. I just don't want you to think that is always the case. It is not. So the first thing they want to do is vertical velocity versus time. Okay, vertical velocity versus time. So the other thing that is affecting our vertical velocity is this little guy, gravity. So he comes into play here because vertically we have a downward pull on any of our objects that are on the earth. So that's going to affect my vertical velocity as well. So when I'm looking at velocity, I am going back to some of my initial equations. So one of my initial equations that we used was the velocity of y. If I am trying to find the final velocity over a period of time, I'm going to take the initial velocity of y, and I'm going to add to it the effect of gravity for however much time it's happening for every second, since gravity is in terms of seconds, right? And so as I calculate this, I am going to calculate it for every single second. That's what they want you to do. So we're going to take this and we're going to fill in this chart for time and then what's happening to the vertical velocity over time. And so the very first one, initially, how fast is it going? We've already calculated that. What was the initial velocity vertically for this thing? Yeah, it was 29.4, right? Positive 29.4. We're going to do that because remember, velocity is directional. They were shooting the arrow up in the air, so initially it is going up, right? We will see that change. So after 1 second, I'm going to say, well, my final velocity for y after 1 second. Well, that's going to be my initial velocity, 29.41. And I'm just going to use the 41 just to keep it a little bit closer to actual. Plus my gravity. Well, gravity is always this. And then I'm going to multiply it by that 1 second. Right? And so after 1 second, I am going to still be going up in the air, but a little bit slower because gravity has started to work on my arrow. So what I want you to do is I want you to take that and I want you to fill in the chart all the way down for 2 seconds, 3 seconds, 4 seconds, 5, and 6. You should see a pattern because it is a linear equation here. So you should have gotten that column for those numbers, all right? Now here's where your velocities come into play for position, all right? For position. My velocity is changing for my for my y value, my initial and all that is changing because of gravity. For horizontal, it's not. And so when we're calculating horizontal, we're talking about just position. So let's look at our position equations. All right, first we're going to talk about x, my x position. All right, if I need to figure out where x is, where is it located horizontally, I'm going to start with where did it start out, right? So initially, where was it? They're not giving me a height, so I'm just going to assume ground level. If it's not ground level, which it probably wasn't, but in this situation, we're just going to use 0. Let's say they had a baseball player and they told me that he hit it from, 4 feet in the air. Then I'm going to use that as a position for height. Or if they gave me a horizontal position, I would use that. They didn't. So when they don't give it to you, you're going to assume a 0 position, meaning ground level. All right. So initial position here is going to be 0. I'm adding to it how fast it's going horizontally and then how long it's taking it to go that far. All right. So if I'm trying to figure out how far it's moving horizontally, I'm going to use the horizontal velocity and the time. All right. And so if I took this, my initial is going to be 0. So that's easy. To figure out after 1 second, so my initial position, he's at 0. Well, what happens after 1 second? Well, we're going to go back to that horizontal velocity, which was also 29.41 meters per second. And we're going to multiply it by that 1 second. Well, logic tells us that after 1 second, it should have traveled that far, right? Horizontally, we're just doing horizontal movement here. So from that, fill in the rest of the chart. Horizontally, how far has it moved after 2 seconds, 3 seconds, 4 seconds, and 5 seconds? So y is affected by gravity. So you don't have to go back and forth because the equation takes all of it into account. The only reason we looked at the velocity over change is because we're actually going to graph it. But when you're looking at your position for your final position for y, you have to consider your initial position. I'm writing this down because it won't always be 0. In this case, we're assuming 0 because they didn't tell us a height. But if they told us a height off the ground, we would change that and put the height off the ground as my initial height. It does consider the velocity of my vertical movement over time. And then because that velocity is affected by gravity, this should look familiar. It is affected by gravity just like this. This is the same equation that we used for horizontal launches. The difference is for horizontal launches, this guy was 0 because there was no initial velocity up or down. And we just moved this guy over to figure out how it changed. So like when we were dropping something off a 200-meter cliff, we would do, negative 200 equals 1/2 gravity times squared, right? And that's what we did over and over. But we were doing that because there was no initial velocity. Now we have an initial velocity on y that's going to affect it. So as I calculate this, again, my initial position, unless they tell me otherwise, we're going to assume that it is a 0. So over here, we're going to assume that y initially was 0. And then how is it affected over the course of 1, 2, 3, 4, 5, 6 seconds? So initially, I'm going to say 0. Velocity, I'm going to go back to the velocity I calculated because this is asking for initial velocity here. After 1 second, I'm going to put a 1 in. 1/2, my gravity, again, negative 9.81. And then 1 squared. And I'm going to calculate that movement. And so my y doesn't move the same as my x. You're actually going to see a significant difference in y. The reason is I'm going up with y and gravity's pulling it, so I'm going to come back down. And so something is affecting that velocity. It's not moving as quickly. In fact, it's decelerating, right? It's coming back down. And so you're going to see y completely different than x when you do something like this. So for this first one, you should get approximately 24.5. So go ahead and fill it in for 2, 3, 4, 5, and 6 seconds. Go ahead and figure out what your y is doing over the course of that time period that they gave us. So I want to put in here. So as you look, this, right? The only way this makes sense is if this went into the ground, which I guess is possible for an arrow. But in your rounding, you may see things like this where, okay, this doesn't line up exactly. And this actually has a negative height, which again, could have gone into the ground for all I know. But likely it's in my rounding that something like this is going to happen, right? And so when we start to graph it, you're going to see why I say that. Because what you'll notice about my x continually gets larger, right? Because it is, let's think about shooting an arrow. If I am shooting an arrow, it's going to continually get away from me, right? That direction. Vertically though, what's going to happen to it? It's going to go up and it's going to come back down, right? And so that's what you're going to start seeing. So the two things they asked us to graph was to graph time versus velocity, all right? Specifically vertical velocity. My horizontal is not changing right now. So if I graphed my time with that vertical velocity, that first column, you'll notice I started out just under 30, right? 29.4-ish. After 1 second, my velocity dropped to 19.6. After 2 seconds, it was still going in the positive direction, but it was 9.8. After 3 seconds, it was at 0 velocity or close to it. What does that mean? If my vertical velocity was at 0, what do you think this is? What's happening if my vertical velocity is at 0? It is neither going up or coming down. What is it doing? It's technically turning, yeah, because it stopped moving up or down. We'll see that in this guy here. Think about the arrow, all right? At some point, as it's going up, the velocity has to change from positive to negative, right? Velocity is directional. It's going up, then it's going down, right? At some point, it turns and it is perfectly parallel to the ground, meaning that it is neither moving up or down at that point. It is turning, all right? And so that's what's happening at 3 seconds. It is at its turning point. There's two things that happens at the turning point. One, my velocity changes from positive to negative. Two, I am at the highest point that the arrow will go. At that point, I am at the highest that the arrow will be, okay? After 4 seconds, you'll notice my velocity changes to negative. That's because the arrow is coming back down. 5 seconds negative, 6 seconds negative. All right? So then this compares range. Range is how far it's moving horizontally, to height, how far it's moving vertically. All right? What type of graph does this look like? This looks like a parabola, right? Specifically, this looks like a negative parabola, right? It's pointed down. Does that make sense? Does this look like the path of an arrow that has been shot? You have the arrow, we shoot it. The arrow goes up. What time do you think this is? 3 seconds, right? That's what time we said velocity was 0, and then the arrow comes back down. All right? So if I compare horizontal to vertical, this is what I'm going to see. At the peak, like I mentioned, at the peak of the trajectory, the vertical velocity is 0. It has changed from going positive to negative. Ignoring air resistance and wind. Yes, that is important. The vertical speed is the same at the same height. In the x direction, it is linear. If we were to have graphed our x, you would see that it continually climbed. Remember linear equations, y equals mx plus b. All right, b, that's my initial position horizontally, plus m times x. Well, m in this situation was my velocity, 4x, and then times time. So you basically have your velocity times your time plus your initial position. That is a linear function, mx plus b. However, for the y direction, as you saw from the parabola, it is a quadratic. So your y ends up being a quadratic. We saw that from our initial function. You had a time squared and a time. Remember, anytime you have a variable squared, that is a quadratic. We have factored quadratics. We have solved by factoring quadratics. This is a quadratic. it is squared. All right? So that's what you'll see when you see a horizontal versus a vertical, ignoring wind resistance or any air problems that you have going on, any wind. So range is determined by the time and the horizontal velocity. That's how we figured out how far it was going horizontally. You're going to hear the word range. That is the time and the horizontal velocity. The time of the flight is a function of the initial vertical velocity and the initial height above the ground. Because remember, that's what's going to determine how long it stays in the air. So while my range is based off of the time and the horizontal velocity, the time of the flight is actually a function of my vertical velocity, that initial push on this object vertically, and how high. So initial velocity and height are going to affect the flight time, right? That arrow is going to only stay in the air as long as that vertical velocity allows it to stay in the air. All right? And once gravity has taken its toll on it, it's going to come back down. That's how objects on Earth work. All right? Assuming that it does not have its own propulsion. All right? Which is what we're doing in this chapter. So real-world problems do have to account for air resistance, as we saw. Range depends on the launch angle. So if you were to ignore air resistance, the maximum range is going to be at an angle of 45 degrees. So for all my baseball and softball players, your maximum angle is 45 degrees. That is your maximum range, which is what you would probably be looking for in something like a baseball game. Range also depends on the elevation of the launch point. Elevation of the launch point, because that's going to affect the time. All right? An artillery piece fires at an angle of 30 degrees above the horizontal. So this is talking about its horizontal, 30 degrees above its horizontal. You can picture maybe a tank or something, an artillery above it. It would be the horizontal to that base of that nozzle of that gun or that whatever it's shooting here. Okay? So that's where that 30 degree comes into play. Its muzzle is 3 meters above the ground. So this is an initial height here. When the shell exits the barrel, it has a speed of 828 meters per second. How long does it take the shell to hit the ground? And what is the shell's range? How far did the shell make it across? All right, so we're going to use what we know. We're going to figure out what we don't know. So we're going to start with this. That is obviously going to be my theta. My theta is going to be that 30 degrees. The muzzle is 3 meters above the ground. That is my initial Y position. My initial Y position is going to be 3 meters, okay? Since they do not tell me any movement, you assume that your origin is where you're starting from horizontally, all right? You would just drop that right, and you're going to stay horizontally where it's 0. So if I looked at my initial X, we're just going to assume that that is not moving anywhere horizontally. It's just there. It's starting at 0, all right? They did give us one more thing, which is 828 meters per second. That is an initial velocity. So we have to calculate a few things here. We have to calculate my initial vertical and my initial horizontal velocity. So I'm going to take those same rules that I applied before, those same formulas, and I'm going to calculate those. So I'm going to say for initial velocity of X, I'm going to take that 828 meters per second, and I'm going to multiply it by the cosine of my angle. And I'm going to get something like that. And then I'm going to do the same thing for Y, but remember Y is an initial because it will be changed based on gravity. I'm going to do the same thing with my Y, but I'm going to use the sine of 30. So make sure that in your calculator you see where all of those numbers came from. The word how long, what are they looking for there? Time. How long they are looking for time. All right, at this point, only Y can help me with it. Y is what determines the time. That's what that meant. My Y's velocity That's going to help me determine the time, right? And how high it started off the ground, okay? So I'm going to use my equation, my final y equation here. It takes into account your initial y. You add to that your y's initial velocity. So we have our velocity of y times that time. And then we also have 1/2 gravity times squared. That's what I'm going to use. All right, so I'm going to rearrange this because this is a quadratic. When I'm doing a quadratic, which variable do I list first in a quadratic? In standard form. Standard form of a quadratic, I'm going to list the squared first, right? Does that make sense? So I'm going to rewrite this guy and write this first. I'm actually going to go ahead and multiply the 9.81 times 0.5 already, so I can get it to look a little bit nicer. So I'm going to say negative 4.905. That's what happens when you multiply these two numbers, times squared. Then I'm going to write that middle term. Initial velocity I've already calculated. Initial velocity of y was that 414 times my time. And my initial position, well, I've already figured that out too. They gave it to me. That is that 3 meters. That should look like ax squared plus bx plus c. I need to figure out when it hits the ground. How high off the ground is it when it hits the ground? What is my position vertically? If I were to give it a number on the ground, what would it be? 0. So I need to figure out when that equals 0. Now you can go back to, oh, I can solve by factoring and by completing the square. I'm sure that's how you choose this. But anytime you're given something like this, you're going to want to use the quadratic formula. All right? So you have to know the quadratic formula, which you all should know at this point in your life. Negative b plus or minus the square root of b squared minus 4ac all over 2a. All right? Which means in your calculator, you need to do negative b plus the square root over 2a. Get that answer. And negative b minus the square root of that over 2a. So what's going to happen here is some answers are going to make sense and some answers are not going to make sense. There are going to be times when it gives you 0 and it gives you some time. There are going to be times when it gives you a negative time, which is not, we're like, that doesn't make sense. And then it's going to give you a positive. All right, so you're going to see that one of these makes sense and one of them doesn't. So go ahead and do that. I'm actually going to give you this so you have a chance to do one. If you do this, you will get either 0 seconds or 84.4 seconds, which makes sense for how long it was in the air. Which of those times? 84.4 seconds, all right? So that is how long it takes for it to hit the ground. 84.4 seconds. The second question says, what is its range? So here's where we go back to our other formula, our x formula. So if I need to find out its final position for x, I do the initial position plus the velocity of x times how long x was in the air. Initially, x was just at 0, right? 0. My x velocity, I calculated 717. And then I'm going to multiply it by how long it was in the air, 84.4 seconds. And from that, with 3 significant digits, you should get that it traveled 60.5 meters. 60.5 meters. Yeah, so if you wrote it in meters, you're going to get a huge number. So in meters, you're going to get 60,514 meters. If you write it in meters, that's fine. Just write 2 significant digits. 3 significant digits. So you're going to do 6,500 meters. I just wrote it in kilometers because it was so big. So just make sure if you do meters, you zero those out and you have 3 significant digits there too, right?